All right, looks like some of you got the results. So hopefully for this one you got 0.3139 or something like that, which can be rounded up to 14. 314. If you got something different, double check your inputs. Did you type the correct fractions? So that's the result here. Now on the other hand, they're asking us to compare this result using the FNINT function. So let's see FNINT. And for the FNINT function, all we have to do is the following: is go to math. Okay. My calculator is not working. Okay. Okay, so go math and FNINT.
Press the number 9.
Yes, number 9. I always forget that one. And that's from 0 to 1. And that's a sine of x squared. And with respect x. And 0.310 is the result using. So those two results, trapezoid rule, FNINT rule, also because we're working on a trigonometric function, make sure that your calculator is set in radian mode.
Can you enter into the calculator for the trapezoid one?
For trapezoid, want me to do it? Okay, let's see. So let me do the input. So it's a 1/10 first. 1/10. Open parentheses. Alpha trace. Enter, in this case evaluated at 0, right? Plus 2 times alpha trace.
I think I just forgot the 0.
You forgot the 0? Oh, okay, so that's why. Okay, but let me do the whole thing just in case. That's 1/5. Oops. Plus 2 times alpha trace evaluated at 2/5 plus 2 times alpha trace, enter, 3/5 plus oh, I forgot a parentheses. Plus 2 times alpha trace, enter, and that's a 4/5, close parentheses, and the last one doesn't get multiplied by 2. That is alpha trace of 1. And wait, why did I get a different result? Oh, mode. So it's also in radians. Did I miss anything? Because I did it on my calculator here by hand. And oh, I don't think I did. Yes, I didn't change the function. Okay, let me change it. That explains a lot. So that's supposed to be sine. Okay, clear. Sine x squared. Second quit. And perfect. There it is. All right. So, okay, let me go back to the notes. So it's great that I did it again, so you can see the potential when you go back and see the video, so you can see the potential pitfalls here, like you forget to change the function that you're working with. Maybe over here some of you like forgot to evaluate the function at the lowest, which is the 0, so that's something that we need to be very careful of. Okay, the Simpsons rule. So let's compare the three different pictures. Well, so in this case, well, the very first method we looked at was to find areas under rectangle. I mean, by approximating areas of rectangles. The second case, which is finding areas under trapezoids, or areas of trapezoids, which is really areas under straight lines. And then the next method, which is the parabola, because in this case for the Simpsons rule we are finding areas under parabola. So what we're doing is in a way sectioning some function f of x. So we have some parabola here, another parabola there, another parabola here. So we're finding areas under parabola. So I think we can see the pattern here, because these are horizontal lines, right? The top parts of these rectangles, but aren't those horizontal lines basically polynomials of 0 degree? And well, what about these lines? These are polynomials of first degree. What about these parabolas? Aren't they polynomials of second degree? Well, when you get to numerical analysis or numerical method, you're going to look at even more methods. One of them is called cubic splines. The other one is called numerical quadrature, and a lot of very interesting methods. And they're not only to evaluate integrals in numerical form, but also to find solutions of other very funky looking equations. So, but for now we're going to stop it here at the Simpsons rule. And well, the formula is very similar to that of the trapezoid rule, but instead of dividing this delta x by 2, we divide it by 3. That's the one difference. The other difference is in this case we need to have an even number of subdivision in this case, because we want to make sure that the middle terms on the expansion inside of these parentheses or these brackets, we get 4, 2, and the second to the last it's also a 4. If in this case we have an odd number, then we cannot end this at 4. So that's why we have to get an even number. Alright, so you'll see how this works. So let's see, let's use the Simpsons rule for the previous example, the integral of 1 plus, well, from 0 to 1 of sine of x squared, and then of course let's round it to 3 decimal places and compare our result with f and I and t. Alright, so in this case, let me draw the same picture again, the same graph. But in this case, I'm going to divide from 0 to 1, dividing this by 6. Every width will be 1/6, 2/6. I know this reduces to 1/3, but let's keep it in terms of sixths. 3/6, that reduces to 1/2, but let's keep it as 3/6. 4/6, 5/6, and 6/6, which is 1. This one we can write it as 1. Now, in order to use, in this case, the Simpsons formula, so area equals the integral from 0 to 1 sine x squared dx. That'll be delta x over 3. The first one doesn't get multiplied by anything, that is f of 0, plus 4 f of 1/6 plus 2 f of 2/6 plus 3, not 3, actually plus another 4 f of 3/6 plus 2 f of 4/6 plus 4 f of 5 over 6, and the last one doesn't get multiplied as well as just like the first one, f of 1. All right, so here's the thing again. The delta x gets divided by 3 instead of 2, and for the middle, except the first and the last one, we get alternating 4, 2, 4, 2, and the last one has to be a 4. So that's why we have to have an even number, because otherwise with an odd number we would end up with 2 only. So be careful here. Okay, so delta x, which in this case, as usual, b minus a over n, that's a 1 minus 0 over 6. That's why we have a 1/6 for each, right? And then 1/6 over 3, isn't it 1 over 18? Okay, let me just do 1 over 18. All right, 1 over 18. And let's just write down the approximated answer. So you want me to do it here on the simulator? Why not? Okay, so that's number 1, 1 over 18, open parentheses, alpha, trace, enter, that gets evaluated at 0, plus 4 times alpha, trace, enter, and that's 1 over 6, and plus the next factor is a 2, alpha, trace, enter, evaluated at 2 over 6. Okay, we already used the 2. Let's use again the factor of 4 plus 4 times alpha, trace, enter, 3 over 6, and plus 2 alpha, trace, enter, open parenthesis, 4 over 6, and plus 4 alpha, trace, enter, open parenthesis, 5 over 6, and we're going to write the last one, but the last one doesn't require any factors, right? So that's just alpha, trace, enter, evaluated at 1. Okay, close parenthesis. For the whole thing, we should get a 0.310. Very similar result than the one we obtained before, isn't it? In fact, it's a lot better. It's closer to even the f and int value. Do you see this value right here? Do you see the value using the f and int? So what are we doing? We're finding the area under the curve by finding the areas of 5, okay, that's 6 parabolas. That's what we're doing here. All right, so 0.310. All right, and of course that's very similar to the result using f and int. All right, so let's talk about error analysis just a little bit. Because of course these are approximation techniques, we need to have an idea of how bad are these approximations, or how good, well, depending on the point of view. And well, we have a couple of formulas here that will help us see how do we find those results, how do we visualize this. Well, in this case, well, the absolute, we use this absolute value bars because, for example, if we're getting a value, that means that value is plus or minus some margin of error, right? So we need to look at both endpoints of the error, and it's given by this expression b minus a cubed over 24n squared, and times max of the second derivative and max of the fourth derivative of the for the error approximating that we using the Simpsons rule. So the first two formulas are, number one, for the midpoint rule, EM. The second formula is to find the error by using the trapezoid rule, and the last formula right there is to find the error by using only the Simpsons rule. All right. So this notation, this max notation might be a little bit new for you. You may not have seen it before. So that means we need to find the maximum of the second derivative, the maximum of the fourth derivative. So we need to take a few derivatives of the given function that we want to integrate. And that's where, well, hopefully the function is not too crazy to differentiate, because if you're given like a quotient function, imagine having to take the fourth derivative of how many quotient rules? Well, many quotient rules you will have to do there, and that's going to be tedious. So to illustrate this example, I'm going to go over an easier function, a nicer function that is easier to find. Well, number one, let's start by finding the four derivatives. So the first derivative of e to the x is 2e to the x, 2x. The second derivative, that's 2 times 2 equals to 4e to the 2x. The third derivative, that's 8. That's an 8e to the 2x. And the fourth derivative equals, that's 16e to the 2x. Okay, so we are going to need these four derivatives because we will find the maximum of the values within the interval. And well, instead of doing that table to get the max and min, we're going to use the graph to see this. You'll see. All right, so let's see. So let's determine the maximum amount of error in approximating this integral from 0 to 1 of e to the x, e to the 2x with respect x, if the trapezoid rule is used with 4 subdivisions, and if the Simpsons rule is used with 4 subdivisions. Okay, so let's write down the formula for the, it's not the mean point, it's the trapezoid rule. So E sub t for trapezoid, which is less than or equal b minus a cubed over 12 and squared times the max of the second derivative. Okay, now what are those numbers? So number one, b minus a, that's easy, 1 minus 0 cubed, and 12 times n squared, which in this case is 4 squared. And then, well, what about the max of f double prime? No, we don't have to go through the calculus. We can just graph this function. You know, the advantage of this example is that when we graph this function, the exponential function pretty much will look always the same, except the y-intercept is what it changes. So, for example, it looks like this, right? And of course, we're looking at 0, between 0 and 1. Okay? So here we need to make a decision. Okay, let's look at the second derivative. The second derivative evaluated at 0 would give me 4 times e to the 2 times 0, which is basically 4 times 1, which is 4. And then if we evaluate at the end point, at the upper end point, which is 1, that's going to give us another value. The question here is, which one is going to give us a largest value? Evaluating it at 0 or evaluating it at 1? So that's the maximum. So no need to set the derivative equal to 0, go through the table to determine max and min, increasing, decreasing. No need. From the graph. I think from the graph it should be clear that one value is larger than the other one, and in this case, the one evaluated at 1 is the maximum. That is, and I'm going to, because it's on the second derivative, I'm going to use this for e to the 2 times 1, which is really 4 e to the second power. Alright? And approximating this result, we should get number one, this is still equal to 4e squared over 192. And well, this is, in this case, approximately 0.154. Okay, that means that the error of using the trapezoid rule is between or the absolute value is less than 0.15 and 154, or if you expand this inequality, it's plus or minus Now, what does that number mean? This number means that the error so the worst error is 15.4%. So in the worst case scenario, using the trapezoid rule with 4 subdivisions, the actual value will differ about 15.4% with respect to the actual value. So that's what this means. Alright? And then in a very similar way, we can use the Simpsons Rule expression, so the one that involves the fourth derivative and some different number. So just e, there's no es, it's just e, less than or equal b minus a to the 5th power over 180 n to the 4th power, and in this case it is times the maximum of the 4th derivative. Okay, which in this case again 1 minus 0 to the 5th, 180 times n, which is 4 to the 5th, big number in the denominator. Now let's look at the 4th derivative. For the 4th derivative, we got 16 e to the 2x, whose graph looks like this. Again, all it changes is the y-intercept. And likewise, evaluating at 0, it's not going to give us the maximum on the interval. That's actually the minimum. And the maximum, again, is going to be given when we evaluate the function at x equals to 1. So that'll be 16 times e to the 2, e to the 2nd, which in this case I got whatever that number is, doesn't matter. After just simplifying this is approximately 0.0025. Well, what does that mean? This means that the error of using the Simpsons rule is 0.25%. Not even 1% error. See how more accurate this result is? I mean, look at trapezoid rule. Same number of 4 subdivisions. But in this case, for comparing with the Simpsons rule, it's a lot better approximation of 0.25. Of course, if we add maybe more subdivision, this number has to be even smaller than that. All right?